Hey guys, Alexander here, and in this video we will be covering continuous distributions in R. In particular, we will be focusing on the uniform, exponential, gamma, and normal distributions. The content that we'll cover will be about probability density functions, cumulative distribution functions, and moment generating functions. So firstly, it's important to ensure that the necessary packages are installed and loaded, and that you should uncomment these as needed just to install the packages and then put the hashtag back or the comment. So we will load the library dev tools so that we can load the package mgf, or install it rather, library stack, so that we can actually work with the PDF, CDF of the various distributions. We will also make use of the library ngf so that we can calculate the moment generating functions of the various distributions. So let's get started off with the uniform distribution. Your friend's lateness to parties is modeled by the uniform distribution, with him being equally likely to be 0 to 10 minutes late. So that would mean that the random variable x, which is how late he is, follows the uniform distribution with a lower value of 0 and an upper value of 10, or a maximum. So when we ask what is the probability that you have to wait more than 5 minutes for your friend, well, annotate that for us. What is the probability that x is greater than 5? And this is simply going to be the integration from 5 to 10 of 1 over 10 minus 0 dx. But that's how we do it with the integration part. But we have RStudio to help us, and we have the stats library to help us. So we don't need to go evaluate this integral. You always need to know about it, but this is what we are simply going to submit. So let's submit that line of code. So P is for the probability. This is equivalent to the CDF. P is equivalent to the CDF. So we are interested in the probability that x is greater than 5. So Q is equal to 5. We're looking for anything from 5 and above, and that's why we need to make use of this lower tail is equal to false. This lower tail equals to false means we are not interested in any value below Q. We are interested in the values above. So anything from 5 all the way to 10. So let's submit this, and we find that the probability is in fact 0.5, which makes sense because if it's uniformly distributed from 0 to 10, 5 is exactly in the middle, and that means that 50% is above, 50% is below that. So next, a typical question that you will get asked is, what's the probability that you have to wait between two values? So from 5 to 7 minutes. So from 5 to 7, we are going to use two calls of the punif function, which means the probability for a uniform distributed random variable to be less than or equal to or greater than or equal to q. So punif with q being equal to 7 and with q being equal to 5. And if we were to draw this, it would be akin to us looking at this diagram. So this is from 0, this is 10, and this is all a tenth. Each of these, this is a horizontal line at y equals a tenth. So we are interested in the value or the area between 5 to 7. So this is the probability that we're interested in. So what we can do is we can take the probability that x is less than or equal to 7, and so because that's this whole area over here, and then we go and subtract that from, so we subtract from it the probability that x is less than or equal to 5, which is this area over here. So then we will be left with the probability that x is less than 7 but greater than 5. So let's submit these two lines of code. And we find that the answer is 0.2. And that makes sense because it's from 5 to 7, and it's all distributed uniformly from 0 to 10. So it's 7 over 10 minus 5 over 10, and that leaves us with 0.2. So that's how we use the uniform distribution in R. Now, there are various other functions, dunif, which returns the exact probability, and we say, let's say x is 1, the minimum is equal to 0, and our maximum is equal to 10, because x is uniformly distributed from 0 to 10, but this will simply just give us 1 over 10 or 0.1, because it's a constant probability of a tenth over all the values from 0 to 10. So let's move on to the exponential distribution. So the exponential distribution is useful as well when we're modeling time between the arrival of events, where those arrivals themselves follow the Poisson distribution. So suppose we are waiting in a queue to be served at a restaurant, where the amount of time between people being served follows an exponential distribution with a mean time of 5 minutes per person. So further, assume that there's one person ahead of us. So we are just waiting for one person to get served and be finished serving. And then we will let x be the amount of time we wait until we get served. So x is going to follow the exponential distribution with a rate parameter of 1 over 5. And you might ask, why is it 1 over 5? Because we have already said that the mean, so the expected value of x, is equal to 5 minutes. And if you remember, if a random variable x follows the exponential distribution with a rate parameter of lambda, the expected value of x is always equal to 1 over lambda. So that means that lambda is in this case going to be equal to 1 over 5. So let's get back to the code part. The exponential example that we'll be dealing with first is, what's the probability that we will have to wait for at most 6 minutes? At most 6 minutes means that the probability that x is less than or equal to 6. So we need to use, if it's less than or equal, you use lower tail equals true. You can also leave out this lower tail equals true, because the default value of lower dot tail is set to be true in the code. So px, or the probability for an exponential random variable with a rate parameter of 0.2 to be less than or equal to 6, is equal to 0.6988058. So that's the equivalent to the CDF with the probability that x is less than or equal to 6. The next question that you get is us using, what is the probability that it will take longer than 6 minutes for us to be served? Longer than 6 minutes, so that means the probability that x is greater than 6. So there are two ways in which we can approach this. We already found the probability that we'll have to wait at most 6, which is the lower tail value. So we can use 1 minus this value. We use the fact of a complement to create this, and we find the answer to be 0.3011942, which we see if it was added to this value, this will add up to 1, because this is the probability that x is greater than 6. But we're using the complement over here. But the smarter way to go about doing this is we set the lower tail to be false. That means we're concerned with the upper tail, the probability that x is greater than q. And if we submit this line of code, we see that the answer is the same. So indeed, you can use the lower tail equals true and the comp together with the idea of a complement, because the probabilities have to add up to 1. And then you subtract, you take 1 and you subtract this from it. Or you can use simply that probability with q equals 6 and you set the lower tail argument to false. Now, using the moment generating function package that I've written, we can directly check the moment generating function of an exponentially distributed random variable. All you do is you say mgf and you type as a string exponential. And we get that it's lambda over lambda minus d. Now let's go evaluate the second moment and the second centralized moment, which is the same as the variance for the exponential distribution using the mgf evaluator function. So we call the function mgf evaluator with the distribution set to exponential, lambda being set to be 0.2, and the order of the moment is 2 because we're interested in the second moment. So once we've submitted this, we get this whole line of code over here. So we see that the moment generating function for the exponential distribution is lambda over lambda minus t. The formula for the second moment is this. This is the formula for the second moment before we have solved for t equals to 0. And the value of the second moment is 50. This is the same as the expected value of x squared if x follows exponential distribution with a rate parameter of 1 over 5. The formula of the second centralized moment, which will be the formula for the variance, is given by this. And if you plug in t equals to 0, this should simplify to 1 over lambda squared. And the second centralized moment's value is 25. And let's check if this does in fact make sense. If a random variable x follows the exponential distribution with the right parameter of lambda, the variance of x is always going to be equal to 1 over lambda squared. So we have 1 over 5 squared, which is equal to 1 over a 25th, which is equal to 25. So indeed it is correct. So that's the various codes and ways in which we can use and solve for the exponential distribution in R using both the MGF package library and the stats library, and using our knowledge of statistics to aid us in computing these values. And this is very helpful if you have to work on assignments or you have any tests that you are practicing for and you want to check for yourself, am I actually deriving the things correctly? So let's move on to the gamma distribution. If a random variable x follows the gamma distribution with alpha and lambda being the parameters, where alpha is the shape parameter and lambda is commonly referred to as the rate parameter, then we can notice something very important. We should note that the exponential distribution is a special case of the gamma distribution with alpha or the shape parameter being set to 1. We can verify this by looking at the moment generating function of a gamma and exponential random variable with the same rate parameters and alpha or shape equal to 1. So gamma distribution MGF, let's type that in over here. And exponential distribution MGF, in fact, let's expand the console over here. And then we should focus on the segment down here. So we see that the MGF for gamma distribution is lambda over lambda minus t to the power of alpha. The MGF for an exponential distribution is lambda over lambda minus t. And can you see that this is just the same as lambda over lambda minus t to the power of alpha, but we set alpha equal to 1. So if we have a gamma distributed random variable, and we set the shape parameter equal to 1, if we set alpha equal to 1, then we will just have an exponentially distributed random variable with a rate parameter of lambda. So an exponentially distributed random variable with a rate parameter of lambda is equivalent to a gamma distributed random variable with 1 and lambda being its shape and rate parameters respectively. So by using the MGF package, you can clearly see and compare and notice the similarities and differences between distributions by simply calling the MGF function, so that we can compare the moment generating functions and actually see for ourselves and convince ourselves that they are in fact similar distributions or they are related to each other. For the rest of the gamma distributed random variable example, assume that x follows the gamma distribution with a shape parameter of 2 and a rate parameter of 0.2. So what is the probability that x is less than or equal to 6? Well, again, we're just going to call the p gamma function with q set equal to 6, the shape equal to 2, and the rate equal to 0.2. Notice that I've left out the lower dot tail over here because the default value of it is in fact true. So if we call this we will see that the answer is the probability that x is less than or equal to 6 is equal to 0.3373727. What's the probability that x is greater than 6? Simply change the lower dot tail argument's value to false. So then we will look at the upper tail value, or the probability that x is greater than 6, and that yields 0.6626273. And just so that I can show you that I'm not lying to you, if we add these two up, they should add up to 1. And over here we can see that that is indeed the case. Lastly, if you ever have to deal with examples where you have to get the probability that the random variable is less than some value and greater than some value, always go and think about your distribution. So the probability that x is going to be less than 12 is going to be larger than the probability that x is less than 6. So we can go and say the probability that x is less than or equal to 12 and greater than or equal to 6. This is simply an integral from 6 all the way to 12 of f of x dx. And to do this in R, all we need to do is we take the p gamma function. We put the upper bound here, and the lower one we put in the second, after the minus sign. So we have p gamma with q equal to 12, the shape parameter to rate parameter of 0.2, and we subtract from that the probability that x is less than or equal to 6, or less than 6, with a shape equal to 2 and a rate equal to 2. Calling this function, we're getting the probability that the random variable x lies between 6 and 12, and the answer that it gives us is 0.3541862. So that's how we calculate the probability that a random variable falls between two bounds using R and using the built-in functions from the statistics library. So lastly, we will be talking about the normal distribution. In this question, assume that the IQ of students in a class follow the normal distribution with a mean of 100 and a standard deviation of 15. That means that our variance is going to be 15 squared, or 225. So if x follows the normal distribution with a mean of 100 and a variance of 225, what is the percentage of students that have an IQ lower than 130? So we assign this to a random variable a, or to a value a. A is the probability that our normally distributed random variable is less than or equal to 130 with a mean of 100 and a standard deviation of 15. And we have the lower tail equal to true because we're interested in the probability that it's less than or equal to 130. So over here in the global environment, or we can just print out the value of a, we see that there are at approximately 97.72% of the class have IQ values less than or equal to 130. So how do we get z-scores corresponding to probabilities if we're dealing with the normal distribution? We simply call the q-norm function with that particular probability in mind. So a is the probability that the random variable x is less than or equal to 130. So if we were to deal with the z-scores for a standard normally distributed random variable, what is the probability, what is the z-score corresponding to a? And we find that to be 2. So positive 2. That means that 130 is 2 standard deviations above the mean of 100, which is the case because 100 plus 2 times 15 is equal to 130. As we go down, we are interested in the probability that students have IQ scores within 3 standard deviations of the mean. So the probability that x is less than 100 plus 3 standard deviations and greater than 100 minus 3 standard deviations. And similarly, we call the p-norm function with the upper bound first, and we subtract from it the p-norm function with the lower bound. And we find this answer to be 99.73% approximately. So within 3 standard deviations from your mean, roughly around 99.73% of your values will lie. So how will we get the moment generating function for the normal distribution in R? We'll simply call MGF normal. And then we will see that it is e to the mu t plus 0.5 sigma times sigma squared times t squared. And if you ever have to go evaluate or calculate the moments of the normal distribution, I highly recommend you to use the MGF evaluator function, because it will allow you to check if your derivations are correct, and it's substantially more convenient than having to do all the derivation by hand and then not being sure if you're correct at all. So let's find the second moments of the normal distribution with a mean of 100 and a standard deviation of 15. And the answer that the code generates for us is the moment generating function for the normal distribution is e to the mu t plus 0.5 times sigma squared t squared. This value over here is the formula for the second moment, so the expected value of x squared. If you go and plug in t equals to 0, you can derive a formula for that, for the second moment in terms of mu and sigma. The value of the second moment is going to be 10.225. And the formula of the second centralized moment is 0.5 times sigma squared times 2, which evaluates to 0.5 times 2 is 1 times sigma squared. So the formula of the second centralized moment is sigma squared, which is the variance. And the second centralized moment's value is the value of the variance, which is 225. So thank you very much for watching this video. I hope it's helped further your understanding of statistics and how you can use R programming, the R programming language, to make your life easier in your statistics courses. Boer Commander out.